Hello everyone. From today I will be starting a new short course on Ising model. So many of my subscribers have requested me to make a video on Ising model, but I thought that it will be good to make a short course on Ising model because there will be many questions and there will be many doubts. So that's why I have decided to make a short course on Ising model, and this is basically the course overview. So in the first lecture, I will be mostly talking about the background, the origin of the Ising Hamiltonian, what is spontaneous magnetization, phase transition, phase, Pochen symmetry, phase transition, and then I will also solve some problems on the Ising model, and I will also write a simple code to check the energy of the Ising model Hamiltonian, and also I will show this application of the Ising model in various fields like biology to StatMech. In my second lecture, I will be deriving the one-dimensional Ising model using the transfer matrix method. I will derive the analytical formula, and in lecture 3, I will write the code for one-dimensional Ising model, and I will be matching the results of the derived formulas in lecture 2, and I will explain it. In the lecture 4, I will derive the formula using Onsager's approach in Ising model 2D, and in lecture 5 I will write the code for the 2D Ising model, and I will match the result with my derived formula in lecture 4, and I will explain it. And lastly, I will also talking about the mean field theory of Ising model. So this is basically the overall course overview for this Ising model course, and please share the course information to your friends and also among your colleagues, and if you are new to my channel, please subscribe to my channel to support me. And so let's start. So you all know about phase, right? So every day in our everyday life we drink water, we eat some solid object like rice or everything. So everything is associated with a phase. So what is a phase? So what is a phase, right? So this is the question. So you all know what is a phase, right? So you can say that a phase is a uniform state of matter, right? You can say that. But so is this complete definition? So the answer is no, because of the following reason. So let's say, let's say you have a gas at some temperature. So then this is also a different uniform state of matter because it is a different temperature. So then this is also a different state of matter because it is at a different temperature, right? But is it the case? So this cannot be true, right? So this cannot be true. So this cannot be true. So because we don't want this type of definition, right? So because we want gas to be gas, solid to be solid, and liquid to be liquid. So what is a particular or what is a complete definition? So the complete definition is the following. So the complete definition is it is a state of matter. So a phase is a state of matter whose properties whose properties vary smoothly. That means it is a function. It is a exact function of pressure, volume, and temperature. So this is a complete definition. So and this also excludes this idea of a different state of matter, like a gas has a different temperature is also always a gas, always in a gas phase. So this is a complete definition of a phase. So you can now define a liquid phase, you can define a solid phase, you can define a gas phase using this definition. So it's a state of matter whose properties vary smoothly, and it is a exact function of pressure, volume, and temperature. So now you have the idea clear that you have three different you have this different type of phases, and mostly the phases that we see in our everyday life, you have this ice, which is solid, you have this water, which is liquid, you have this gas, or maybe I can say that water vapor, which is gas, right? So these are the three phases of matter that you saw every day in your daily life. And going from ice to water, what you have to do? Let's say you have ice, what will do to make it water? So you will heat it, and this is basically a phase transition from solid phase to liquid phase. Whenever you heat it, you will make the ice water, and this is you change the phase of the matter. And again you have the liquid, and again you heat if you heat it. So then also it is a phase transition, and this is from liquid phase to gas phase. Now what will happen if you cool it instead of heating? So if you cool the water vapor, and it will initially go to the water phase if you cool the water vapor. So if you cool it, so it will be water from water vapor to water, and this is also a phase transition. And if you again cool it further, and this will again water become ice, and this is also become a phase transition. So now this is basically the particular picture of phase transition. And so whenever a phase of matter changes to another phase of matter, so the phase transition occurs. So and also we need to know what defines the phase transition, what are the properties that changes in the phase transition, and what defines the you may have heard about the first order phase transition, second order phase transition, what defines the order of the phase transition. So that I'll just talk in a while. Before that, so in this to describe this phase transition type of thing, so physicists have taken two approaches. So the first approach is to take different ensemble for different phase. So you have a particular ensemble for gas, you have a particular ensemble for solid, you have a particular ensemble for liquid as well. So now for gas, you know that so the atoms are non-interacting, right? Right, but in this case, this approximation in this case is not true, because in solid the atoms you cannot take the approximations this. So in case of solid, so let me introduce a new page. So in case of solid, so non-interacting atoms, or atoms with negligible interaction, so that is a very good approximation, or you can say excellent approximation, very good approximation for gas, but it's a very bad approximation for solid. because of the following reason, that in gas the atoms are disordered and they are moving here and there. If you can see this picture, you can see this. In case of solid, the atoms are ordered because they are ordered in a several fashion, ordered in a particular fashion, and here the atoms are disordered because there is no particular order associated with that. Similarly in the gas phase. So in solid phase also you can see the solidized is a particular order. In if you warm it, it will become liquid water, and then the atom will be disordered, and in gas phase it will be more disordered. So if you increase the temperature, and this is how the phase transition occurs. So now this approximation of the negligible interaction is a very good approximation for gas, but it's a very bad approximation for solid, and that's why we took different ensemble for different phase, which is one particular ensemble for gas, particular ensemble for solid, and particular ensemble for liquid. And the definition of ensemble is basically the identical copies of the particular system or particular phase. Let's say if you have a liquid phase which has a particular PVT, and you make identical copies of that ensemble, identical copies of the ensemble of such of that phase, and that is basically the ensemble. And the second approach is basically the following. So if you know the partition function, if we know the partition function of a phase, then you can approximate the partition function of other phases. So the for example, let's say you know the partition function z, so for water. So you know the partition function z for water, and now from here you can approximate the partition. You can approximate the z of ice, also z of liquid, and so on. So now the point is that, let's say so if this z can capture all the three phases, then you can be so sure that z must have non-smooth properties. So it must have non-smooth properties. Why is that? Because if you have a exact partition function for water, and if you want to approximate it for ice and liquid, then what will happen is that going from water to ice, you have some discontinuity, because you are going from one phase to another, and that discontinuity should be incorporated in the partition function, and that will show some non-smooth properties, because if we go from it will show non-smooth properties when you will go to one phase to other. So then only it will show non-smooth properties. In the temperature, in the pressure, it can, so there will be some temperature pressure associated with the phase transition, and that will show and that basically this partition function will show these non-smooth properties. And this approach is basically there are several examples of this approach, which is renormalization group theory, mean field theory, then your Landau theory, and so on. So these are the two approaches to describe the phase transition and the related phenomena related to phase transition, and these are basically the definition of phase and phase transition. And now I will go to the definition of first order phase transition and second order phase transition, and also I will describe the thermodynamic limit. So talking about the first order and second order phase transition and what defines the phase transition. And so this is basically a classification which is done by Ehrenfest. So write Ehrenfest classification. So what he said? So he said that a phase, a phase transition is labeled as nth order if any nth derivative of free energy, if any derivative of free energy with respect to any of its variable or any of its argument yields a discontinuity or jump, yields a discontinuity or jump, you can say jump at the phase transition. Okay, so what defines the phase transition? So a phase transition is basically, you can say that this is a first order phase transition if the free energy, the first derivative of free energies are discontinuous, and if it's a second order phase transition, then the second order derivative of free energy will be discontinuous. So this is how we define the first order or second order phase transition, like that. And so this basically the definition of the order of the phase transition. And now after defining that, so there is a one quantity which is called the order parameter. So order parameter. So what is order parameter? So a order parameter is an observable that is a measure of the phase transition. So a order parameter is an observable O, let's say, that is a measure of the phase of the system, phase of the system. So the order parameter is basically an observable which is a measure of the phase of the system. So it normally basically ranges from, so it normally ranges between 0 in one phase and non-zero in other. So this is how, so let me introduce a new page. So this is how basically a order parameter works. So let's say if you have a first order phase transition, so if you have a phase transition like this, and so if you plot the order parameter with respect to temperature, let's say, and it will go something like this. It has some value, some non-zero value, and then it will go to 0, and it will go to 0 at some temperature which is called the critical temperature Tc. So for the second order phase, in Ising model there is a transition that I will describe later, which is ferromagnetic to paramagnetic. So this transition is second order, and I will describe why it is second order. So this is a second order phase transition, and this will show a continuous jump. So it will show continuous jump in the order parameter. But if you have a first order phase transition, so this is for second order. So for first order, what we will see is that this jump is discontinuous. So if you plot order parameter with respect to temperature, so then it will be some non-zero value in one phase, and then it will show a discontinuous jump. So this is a discontinuous jump, like liquid to vapor, solid to liquid, like that, discontinuous jump. So like solid, like ice to water, maybe ice to water. So this is how a order parameter works. So in Ising model, the magnetization is basically the order parameter, and that I will describe in a while. And in the Ising model, it goes from 1 to 0, and in the case for ferromagnetic, magnetization is equal to 1, and when it is paramagnetic phase, the magnetization becomes 0, and it will go from 1 to 0. It's a non-zero value to 0 value in non-zero value in one phase, ferromagnetic phase, and 0 value in paramagnetic phase, and that basically defines the. So this is basically the order parameter to characterize the phase transition, and it will show that there is a phase transition which is actually is going on, and this is how basically the thing works, and this is how order parameter basically labeled. Order parameter basically classify the transition of this point. And now the point that I was talking about, that if you have a first order phase transition, and there is a jump in, there is the first order derivative of the free energy is discontinuous. So let me plot something for you. So let's say if you have a first order phase transition, and you know that entropy is basically defined from the first order derivative of the free energy, and that's why entropy will show a jump in the first order phase transition. So if you plot S versus temperature, then at Tc, so this is, let's say, at Tc, so it will show a jump. So it will go like this, and then at Tc it will show a jump, and then it will again like this. So this, whenever there is a jump which is discontinuous, I will draw is as a dotted line, and this is basically a first order phase transition. You can say this is a first order phase transition because F is a first order derivative of the free energy. So this can be, we can define with the first order derivative of free energy, and let's say if you plot for the same thing for the second order phase transition, so S versus T, so then what will happen is that it will continuously go from one phase to another. So this is at Tc. So this is the second order, and you know that for second order, the second order derivative of free energy will be discontinuous, but the first order derivative will be continuous. That's why the entropy, which is defined from the first order derivative of the free energy, is continuous in the second order phase transition, and it is discontinuous in the first order phase transition. But eventually, if you take the second order quantity in the second order phase transition, so that will also show a jump. If you in case of, let's say, Cv, which is defined with the second order derivative with respect to second order derivative of free energy with respect to temperature, and if you plot this Cv, it will show a jump in the second order phase transition. So it will show a jump in the second order because it is a second order derivative of free energy, and from the definition of errant phase, if we have the second order phase transition, then you will get a jump in the second order derivative of free energy, and Cv is calculated using second order derivative of F, which is del 2F by del T2, and S is basically del F by del T, and then you basically if you calculate that, then basically that is will give basically discontinuous jump in the second order derivative. And so this is basically the thing, and okay, so what's next is basically, so for your reference, S is basically defined as minus of del F by del T, which is the first order derivative, and Cv is defined as the minus of T. So it is basically T into del S del T, and del s del t s, you know, this thing. So minus of t del 2f by del t2. So this is the quantity. You can see this is a second order derivative, and as it is a second order quantity, this will show a jump in the second order phase transition. And this is the thing basically, which I was trying to say. So this is basically the thing, and now you have the idea clear, which is first order phase transition and what is second order phase transition. And there is another point, which is if you have a first order phase transition, then there will be latent heat associated with that. But if you are second order, but no latent heat in second order phase transition. So that is the thing basically. So what is the latent heat? So in let's say if you have some so if you have some water and then you make it ice, and there will be a jump in the delta S, right? So that I just saw that there is a jump in delta S. So let me introduce a page. So in first order, PT means phase transition. So delta S is discontinuous, right? Because this is the first order derivative of the free energy. So delta S is discontinuous because this delta S, so going from, let's say, liquid to solid, so there is delta S will be SL minus SS, which is the entropy of the liquid and entropy of the solid, and we are subtracting from liquid to solid because entropy in the liquid state will be more than the entropy in the solid state, because in the solid state the system is ordered and in the liquid state system is disordered. That's why more disordered means more entropy, and that's why the entropy of the liquid state will be higher, and this quantity will be SL minus SS. And the latent heat is basically, so the latent heat is basically equal to L equal to T into delta S. So this is basically the quantity. So there will be this thing associated with a phase transition in the first order. So to understand this, suppose you had heat to a block of ice at a constant rate, and its temperature increases steadily until it will reach 0 degree Celsius, and where the temperature stays put until the ice is all melted, and all the heat we put in at 0 degree Celsius goes into melting the ice, and this heat is the latent heat of transformation, right? So going from 0 degree Celsius 0 degree Celsius water to 0 degree Celsius ice is basically you need latent heat to be extracted. So that is the thing. Similarly, for the 100 degree Celsius water to 100 degree Celsius water vapor. So going from this to this needs a latent heat, and that is a transition. So you can have 100 degree water at 100 degree Celsius, but you just the heat you need, the heat you needed or heat you need to going from 100 degree Celsius water to 100 degree Celsius water vapor is basically the latent heat. And you know that 100 degree Celsius is the boiling point of the water, and also the 0 degree Celsius is the freezing point of the water. And this is the thing, that you can have water at 0 degree Celsius, and then the heat that it needs to be extracted to make it 0 degree Celsius ice is basically the latent heat of the transformation, which is given by the T into delta S quantity. So that is the thing. So this is basically the thing, but there is no such latent heat related to the second order phase transition, because you know that in second order phase transition is basically the delta S is basically continuous, and there is no point of defining the latent heat. So this is basically the thing. So this is all about the phase transition, order parameter, and phase. And now what I will be next talking about is basically the there is one particular phase transition which is ferromagnetic to paramagnetic phase transition, and this is basically a second order phase transition, because you know already that what is the definition of phase transition, and that behavior is shown by this transition. And if you plot the order parameter, which is the magnetization, if you plot the order parameter of this transition, which is the magnetization of the system, so if you plot the magnetization modulus of the magnetization, then it will go something like this. So it will go from 1 to 0. So 1 in ferromagnetic case and 0 in paramagnetic case. So now what I will do is basically I will try to describe what is ferromagnetic material, what is paramagnetic material, and what is basically the transition is, and this is all about the Ising model. And I will also show that what this Ising model is the simplest possible model which can capture the ferromagnetic to paramagnetic phase transition. And next I will describe the broken symmetry as well. So before going into I forgot to describe one thing, which is basically the symmetry breaking. So phase transition often involve the development of some type of order which is associated with the symmetry breaking. So phase transition often involve the development of some type of order with an associated symmetry breaking. So what is symmetry breaking? That we need to understand. And this symmetry breaking is described by the order parameter that I just described. So this symmetry breaking is described by the order parameter. So now what is symmetry breaking? So when when we go from one phase to another, which symmetry is broken? So that we need to understand. So let me go to the picture. So in this picture, as you can see, so let's say if we have not this picture. So let's say if you have this picture. So this is a sphere and this is a cube, right? So tell me which are the symmetries both of this system has. So now as you can see in this sphere case, so it can rotate by any angle, right? So in this sphere case, so you can, if you rotate the sphere, if you rotate it, then it will be same as it was earlier. Right? You cannot differentiate between the two configurations if you rotate it any angle. But in the case of cube, you can rotate by some specific angles, like right 90 degree, 180 degree. So for cube, some specific rotation, not all. So by the word some specific rotation, I want to mean that, so if you rotate the cube by 90 degree about its any one of the face, then it will be the same. Even if you rotate it 120 degree or 240 degree about its corner, then it will be the same. if you rotate it 180 degree with any of its edge, then it will be the same. But if you rotate it with any angle, any arbitrary angle, it will not be the same as its earlier configuration, and that is basically the broken symmetry state. So which symmetry is broken from going from this to this? So the rotational symmetry is broken. So here the rotational symmetry is broken. Symmetry is broken. So that's why it is called broken symmetry. So here, going from sphere to cube, we have broken the rotational symmetry. And now next, consider this picture. So in the case of ice, you have this order structure, and in case of water, you have this disorder structure of the molecules. And here you can see, if you translate the molecules of water by some amount, then the configuration will remain the same. And then that's basically water. This liquid water contains the translational symmetry. But if you go to the crystal phase, which is the ice, you can translate by its periodic this lattice spacing, right? Not by any angle, not by any amount of vector. So you can translate by the lattice constant A, but in case of water you can translate by any amount. So water contains the translational symmetry, and going from water to ice, you have broken the translational symmetry. So water to ice, you have broken. So here you have translational symmetry, but here broken. So symmetry is broken, translational. No symmetry is there. So here you can write translational symmetry is broken, because there is no symmetry. You can only shift the ice by some specific amount, not by any arbitrary amount, and that's why it is called broken symmetry state. And this is what is mean. So you may have seen your professor telling that it's a broken symmetry state, or here it's the symmetry is broken going from one phase to another, and that is what it means, that why this thing is called. So in some transition the rotational symmetry will be broken, then and some transition translational symmetry will be broken, like this. So this is how, from going from one phase to another, some symmetry will be broken. And in case of also the ferromagnetic to paramagnetic transition, or maybe paramagnetic to an antiferromagnetic transition, you will broke some symmetry, and that I will describe which type of for that you need to know the Hamiltonian of the system, and you have to characterize the symmetry from the Hamiltonian, and going from one phase to another you can see that some symmetries will be broken in the phase transition, and which can be captured by the order parameter. And now so you know that broken symmetry occurs when ordered ground state doesn't have full symmetry of the Hamiltonian. By the what I mean that let's say if we have symmetries, so whenever there is a symmetries of a Hamiltonian are that associated with a that operators are basically commute with the Hamiltonian. So for example, let's say if we have a homogeneous isotopic liquid which has transitional symmetry, so like water, as I just described, it has transitional symmetry, and or you can say transitional invariance. So you can move all atoms by the same amount, and the liquid looks the same, the water looks the same if you displace the all atoms by some amount, arbitrary amount. But once the system forms a crystal, where the system basically, if you form the crystal, the atoms or the molecules sit on a particular periodic lattice. You can see here it's a periodic lattice, or you can see this picture as well. So whenever it freezes to water freezes to ice, it basically the atoms or molecules sit on a periodic lattice, and the translational invariance is broken, because you cannot you cannot move by arbitrary distance. You cannot move arbitrary distance and get the same structure. you can move only a particular lattice constant, you can move up to a particular lattice constant which is discrete in nature, but the transitional symmetry is broken here. And it basically the Hamiltonian, it contains that, and this is basically the transitional symmetry which is broken going from water to ice. And so this is basically the thing. So if a Hamiltonian has a transitional symmetry, you know that from your classical mechanics, if a Hamiltonian is transitionally invariant, this then basically the momentum is conserved, and the momentum is a good quantum number, and in the Fourier space the states can be labeled by any value of the momentum. But in case of crystal, you have the discrete transitional symmetry, you can go up to a lattice constant, and that is basically in the Fourier space it will give it will basically it will give the discrete values of the momentum. And so it's basically, we saw an example of this when we solve basically the eigenstate of a free particle. Like, so when you solve the eigenstate of a free particle with a periodic boundary condition, and you found that only discrete values of the momentum are allowed, right? So that is basically the thing. So this is basically the symmetry breaking case, and I'll also show that in case of ferromagnetic transition or antiferromagnetic transition, you will see that some symmetries are broken, and that basically the symmetry broken state are basically related to some order parameter. But sometimes the thing is that the finding order parameter is not so easy. So it is basically very difficult to find order parameter. Like in the glass transition problem, in the glassy dynamics problem, the order parameter is still not defined. So order parameter is a very hard thing to define. And so in case of ferromagnetic, so that as I already described, in case of ferromagnetic to paramagnetic transition, so transition, you have the magnetization is the order parameter, which is the sum over all spin values SI, sum over I. And in case of, let's say, the ferroelectric transition, you have this electric polarization, which is the order parameter. In case of liquid crystal, you have the degree of alignment of the molecules as the order parameter, like so on. So this is how basically the thing goes. And so then basically I will describe the ferromagnetic material and also the paramagnetic material, and what are their properties, and then I will go to the derivation of the Ising Hamiltonian, from where it came, and that is basically the schedule.